Intuitionistic fuzzy Beaker method for facility location selection problem. Abstract, the selection of a facility location, which is a kind of multi-criteria decision-making, MCDM, problem, should be considered strategically. The purpose of this paper is to demonstrate and validate the application of the intuitionistic fuzzy Beaker, IF VIKOR, method to solve one problem of real-time location selection of facilities, in which the criteria values are described in exact, crisp, values form. Firstly, the decision matrix is fuzzified and then transformed into an intuitionistic fuzzy decision matrix. The criteria weights are determined using the intuitionistic fuzzy entropy weight method. Euclidean distance measure is used in this work. The ranking performance of IF VIKOR is discussed and compared with the other conventional MCDM methods obtained by past researchers to assess the impact of the IF VIKOR method. It is observed that the ranking largely remains unchanged in almost all the applied methods, and the first two top alternatives exactly match with those as obtained by the past researchers. There exists a high Spearman's rank correlation coefficient value between IF VIKOR method and other conventional methods. The comparative analysis, therefore, confirms that no matter the changes made to the MCDM method and weights of the criteria, crisp and/or if set. Keywords: facility location selection problem, MCDM, IF VIKOR. Introduction. Facility location selection is the determination of a geographic site for a firm's operations. The facility location decision contains organizations looking to locate, relocate, or develop their operations. The facility location decision process includes the identification, analysis, evaluation, and selection of alternatives. 1. Selecting a plant location is a very significant decision for firms because they are costly and difficult to inverse, and they need a long-term guarantee. And also position decisions have an influence on operating costs and profits. For instance, an unfortunate choice of location might result in unnecessary transportation costs, a shortage of qualified labor, loss of competitive advantage, inadequate supplies of raw materials, or some similar condition that would be disadvantageous to operations. There are four famous conventional approaches are usually used in the facility location selection: factor rating system, break-even analysis, centers of gravity method, and transportation method as in 2. Facility location selection is a typical multi-criteria decision-making, MCDM, problem. Past researchers have already applied different conventional MCDM techniques to deal with the facility location selection problems. Reference 3 presented a survey about multiple criteria facility location problems. Reference 4 presented a TOPSIS methodology to find the supportive centers in military logistic systems. Reference 5 considered a facility location selection problem consisting of 6 alternative facility locations and 5 different criteria. Reference 6 applied different crisp decision-making techniques. SAW, weighted product method, WPM, AHP, graph theory, and matrix approach, GTMA, TOPSIS, and modified TOPSIS methods to deal with the facility location selection problem considered as in 5. Reference 7 applied Prometheus 2 method to deal with the same problem. However, a key drawback of the most conventional MCDM approaches is the need for accurate measurement of the performance values and criteria weights. The most conventional MCDM approaches for facility location problems tend to be less effective in dealing with the imprecise or vague nature of the linguistic assessment. In real life, the evaluation data of plant location suitability for various objective criteria, and the weights of the criteria are usually expressed in linguistic terms. And also, to efficiently resolve the ambiguity frequently arising in available information and do more justice to the essential fuzziness in human judgment and preference, the fuzzy set theory has been used to establish an ill-defined multiple criteria decision-making problems. Reference 8 developed a fuzzy SAW for solving facility location selection problems. Reference 9 applied a fuzzy TOPSIS method-based approach to solve the solid waste transshipment site selection problem. Reference 10 focused on the applications of fuzzy AHP and fuzzy TOPSIS methods for solving facility location selection problems. Reference 11 presented a Z-Prometheus with Z numbers as a new representation of vague information for a facility location selection problem. The literature review above indicates that the majority of the previous studies evaluated and selected facility locations under a crisp and fuzzy environment. However, the fuzzy set theory cannot be used to completely tackle vague and imprecise data given by decision makers. The IF set theory has been used to establish an ill-defined facility location selection problem. Reference 12 proposed the IF TOPSIS method for dealing with imprecise information on the facility location selection problem. Given the strengths and wide applications of the Beaker method and IFSS, This paper attempts to bridge the gap in the literature by developing an intuitionistic fuzzy Beaker method for solving facility location selection problems. The primary contributions of the study are summarized as follows: 1. To deal with the uncertainty and vagueness in facility location selection problems. Performance ratings of alternatives are taken as crisp values denoted by if numbers. 2. If entropy weight method is proposed to define criteria weights in solving the selection problems, and 3. To identify the most appropriate location, an extended Beaker method is used for the ranking of the considered alternatives. Furthermore, one empirical example of facility location selection is provided to illustrate the applicability and effectiveness of the IF VIKOR method. The remainder of this paper is organized as follows. Section 2 reviews some basic concepts of IFs. In Section 3, one application example is demonstrated to highlight the applicability of the IF VIKOR method. In Section 4, a comparative analysis is conducted. The final section summarizes the main work of this paper with a discussion of implications for future research. 2 preliminaries. A intuitionistic fuzzy set, IFs. An intuitionistic fuzzy set, in the universe of discourse, is defined as follows: 13. Where 0, 1 respectively represent the membership and non-membership functions on condition that 0 equals plus equals 1. Additionally, IFs introduces a third construct, the intuitionistic fuzzy index, which expresses whether or not belongs to. The intuitionistic index in 2 measures the hesitancy degree of element in where it becomes obvious that 0 equals 1 for each. A small value of implies that information about is more certain. On the other hand, a higher value of the hesitancy degree means the information that holds is more uncertain, and is also frequently referred to as the degree of hesitancy of X to A. It expresses the degree of uncertainty in the assessment as to whether X is, or is not, a member of IFs. B. Construct IF set from crisp set. In this step, IFs can be created by the following sub-steps. Define a universe of discourse for the crisp set by taking their real numerical values. Construct the proper fuzzy sets for each crisp criterion. The process of transforming a crisp value to a fuzzified grade of membership is known as fuzzification. The membership function formation includes graphical representations in the form of different shapes and equations and can be implemented and used. In this work, the vector normalization is used as a membership function. Equals, v, 2, equals 1, 3. Apply the method 14 to construct IFs from Fs obtained in step 2. See intuitionistic fuzzy entropy, IF. Different from the traditional entropy method, IF focuses on the credibility of the input data to determine criteria weights. It measures the extent of separation of the IFs from fuzzy sets rather than from ordinary sets as in the traditional entropy method. Several widely used IF are proposed. Reference 15 derived an entropy value for IFs and the intuitionistic fuzzy entropy weight as in 16. The entropy value for each criterion can be calculated as equals dash 1, 2, plus, dash, 1 dash, 1 dash, dash, 2, equals 1.2. 4. The objective weights of criteria can be evaluated as follows, equals 1 dash, 1 dash, equals 1, equals 1.2. 5. Where is the number of criteria? 2.3 Distance measure between IFs. Let and be two IFs in the universe of discourse, where equals and equals. Several widely used distance measures are proposed. Reference 17 proposed Euclidean distance as 6. 3 IF VIKOR method for MADM. As for reference 18, 19 initially proposed Beaker, VL Skriterihumska optimizacija I kompromisno rešenje, which means multi-criteria optimization and compromise solution. This method focuses on ranking and selecting from a set of alternatives, and determines compromise solutions for a problem with conflicting criteria, which can help the decision makers to reach a final decision. Here, the compromise solution is a feasible solution that is the closest to the ideal, and a compromise means an agreement established by mutual concessions. It introduces the multi-criteria ranking index based on the particular measure of closeness to the ideal. Where equals maximum. Asterisk equals min. Equals maximum, asterisk equals min. Is the coefficient of decision mechanism. The compromise solution can be elected by majority. 0.5, consensus, equals 0.5, or veto. 0.5. Step 5, rank the alternatives and derive the compromise solution. Sort, comma, and in ascending order and generate 3 ranking lists, and such that the lower the value the better the alternative. Then, the alternative that ranks the best in minimum value, and fulfills the following 2 conditions simultaneously would be the compromise solution. Condition 1, acceptable advantage. 1 has Q, A, Q, A. DQ where A is the alternative which is ranked second by Q and DQ equals 1, M1. Condition 2, acceptable stability. The alternative A should also be the best ranked by. And if one of the conditions in step 5 is not satisfied, propose a set of compromise solutions which include alternatives A and A if only condition 2 is not satisfied, or alternatives A, N, if only condition 1 is not satisfied. The closeness of the alternative A, N, ranked nth by Q is determined by Q, A, N, Q, A, DQ for the maximum. For case study illustration. Reference 4 considered a facility location, plant location, selection problem consisting of 6 alternatives, locations, and 5 different criteria. The 5 different criteria are cost of land, C1, cost of energy, C2, cost of raw materials, C3, the cost of transportation, C4, and the cost of labor, C5. All these criteria are non-beneficial where smaller values are desirable. In this work, the Bhattacharya dataset of facility location selection problem is considered as the case study. This MCDM problem is listed in Table 1. Table 1 Quantitative information of Bhattacharya of facility location selection problem. Location. A case study solution. Reference 5 has been solved herein to exhibit the application potential of IF VIKOR. Since the weights of attributes and IF DM are completely unknown, the best alternative would be selected with the information given above. In the following, the IF VIKOR method is applied to solve this problem. The operation process is given below. Phase 1, it is necessary to construct the IF decision matrix and determine the IF entropy weight of each criterion before applying the IF VIKOR. Step 1, constructing the IF decision matrix. Firstly, it is necessary to construct the IF decision matrix from a crisp decision matrix table. 1. Intuitionistic fuzzy decision matrix can be created as the following. Crisp numerical values of each criterion Cj are fuzzified by using vector normalization as the membership function of the fuzzy set. The following fuzzy data values of Cj are obtained and listed in Table 2. Table 2 Fuzzy decision matrix. Location. To apply the method as in 14 as applied by 26 to construct IFSs from FSS obtained in step 1. The IF decision matrix is constructed as showing in Table 3. Table point 3, Intuitionistic fuzzy decision matrix. Step 2, determine the IF entropy weight of each criterion. Based on the objective weighting method, the IF value of each criterion is obtained by 4, and the objective criteria weights are calculated based on 5. Therefore, the weight vector is W equals 0.4174.0.0748.0.1204.0.1410.0.2464. Phase 2, applying the IF VIKOR. Step 1. Determine the best and worst value for all criteria. The best value and the worst value for all criteria can be determined by using 7, and the IF decision matrix table 3, as the following. Plus equals 0.1864.0.6825.0.1312, dot 0.285.0.0.537.0.1780, 0.2818.0.5599.0.1584, dot 0.2771.0.5524.0.1705, dot 0.23660.0.5927.0.1707, equals 0.5312.0.3376.0.1312, dot 0.4219.0.4002.0.1780, dot 0.3981.0.4435.0.1584, 0.4233.0.4062.0.1705, dot 0.4961.0.3332.0.1707. Step 2. Compute the values, and table, for utility value for each criterion SIG and group utility value SI for all alternatives. Location. The group utility value for alternative A1 in table 5 is calculated by using 8, as follows: S1 equals 0.1467 plus 0 plus 0.0085 plus 0.0243 plus 0.0855 equals 0.2649. The same calculation steps can be performed to obtain the group utility value SI for each alternative as given in table 4. The individual regret value R1 for alternative A1 in table 5 is calculated by using 9, as follows: 1 equals 0.1467. The individual regret value Ri for each alternative are presented in table 5. Without loss of generality, let equals 0.5. By using 10, the value of for each alternative can be obtained. The compromise value chi for each alternative are listed in table 5. Table 5, compromise value I for each alternative. Location. Where A, and are the top 3 alternatives in. Step 3. Rank the alternatives and derive the compromise solution. From the table 5, it can be clearly identified that the ranking result based on the measure Q is 521463, reaching the conclusion that A5, minimum Q value, is the best choice and A3 is the worst choice, maximum Q value, for the selection problem. The ranking result based on the measure Q obtained from table 5 has been checked for acceptability conditions. To validate the ranking results based on the measure Q, the 2 already explained conditions required to be satisfied. Condition 1, acceptable advantage. 1 has Q, A, Q, A, DQ. Not satisfied. Condition 2, acceptable stability. The alternative 1 should also be the best ranked by and alternative 1 is the best ranked by S and are satisfied. If one of the above conditions is not satisfied, then a set of compromise solutions is proposed. The condition 1, acceptable advantage, is not satisfied, then alternatives A, and are considered as compromise solutions. A, N, is determined by the relation Q, A, N, Q, A, DQ for maximum N. The positions of these alternatives are in closeness. It can be clearly identified that the ranking result based on the measure Q5 equals 21463 and the alternatives 5 and 2 are only compromised solutions. V. Comparative analysis. References 6 and 7 have already applied different crisp decision-making techniques to deal with the facility location selection problem considered by 5. The results obtained by 6 and 7, and the IF MCDM methods considered in this work are listed in Table 6, and Figure 2. The results show that the ranking remains unchanged in almost all the methods applied by 6 except in the Topsis method where alternative A3 outranks alternative A6 as compared to the other methods as in 6. The ranking order thus obtained through the exploration of the IF VIKOR approach has been compared. It is observed that the 2 top-ranked alternatives A5 and A2 exactly match with those as obtained as in 6 to 7. Table 6, comparative review of obtained results 6 and 7 and the IF MCDM approach. Crisp. It can be seen that ranking largely remains unchanged, especially among the first 2 ideal alternatives. The comparative analysis, therefore, confirms that no matter the changes made to the MCDM methods, crisp and/or IF, and weights of the criteria, traditional and/or IF, alternatives A5 and A2 remain the best alternatives in the selection of facility locations, but it is reflecting on the ranking order of alternatives. Table 7 shows the Spearman's rank correlation coefficient values when the rankings of the alternative facility locations as obtained using IF VIKOR and other MCDM methods as in 6 and 7. It is observed that the Spearman's rank correlation coefficient value ranges from 0.83 to 1. There exists a high Spearman's rank correlation coefficient value between IF VIKOR and SAW, WPM, AHP, GTMA, and M-Topsis methods, which suggests that these 2 MCDM methods are similar regarding their ranking perform. The ranking performance of the IF VIKOR method with respect to other MCDM methods are observed to be quite satisfactory, which asserts the justification that the same can also be applied to other strategic decision-making problems. 6 Conclusions. Since the VIKOR method is an effective MCDM method to reach a compromise solution, and IFs are an effective tool to depict fuzziness and non-specificity in assessment information. This paper combines them to deal with those facility location selection problems in which the importance of criteria are given and described in exact, crisp, values form. To illustrate the feasibility and effectiveness of the proposed IF VIKOR, 5 facility location selection problem is considered in this work, and the obtained result is compared with the other conventional MCDM methods obtained by past researchers. It is observed that the ranking largely remains unchanged in almost all the applied methods, and the first 2 top alternatives exactly match with those as obtained by the past researchers. There exists a high Spearman's rank correlation coefficient value between IF VIKOR method and other conventional methods. The comparative analysis, therefore, confirms that no matter the changes made to the MCDM method and weights of the criteria, crisp and/or if set. Also, the proposed IF VIKOR method is a general method, which can be used for other areas of decision-making problems.